Good evening, good afternoon, and good morning to you eCognition gurus and fans. And welcome to our webinar here for December. We have dubbed this one, What's New in eCognition 9.3, because just a few weeks ago we had the pleasure of releasing our new version of eCognition, and we hope to inform you on some of the highlights that this version 9.3 includes, and get you up to date on new features that are available to you within eCognition Developer. My name is Keith Peterson. I am the product manager for our Trimble eCognition software products, and today I have an honorary guest in the room. It's Christian Beiza, our now market manager for the Trimble eCognition and info products. He will be assisting me in this webinar and then fielding some of the questions that you may have and come up during the course of the webinar. If you do have questions, please feel free to enter these into the question field, and you can ask a question at any time, and we will look into these and hopefully select a few during the presentation, maybe a few in a Q&A session afterwards. If you have to leave at any time for other meetings, don't worry. This session will be recorded and will be available on our webpage afterwards. So again, thank you for taking the time to attend. Title of the presentation, What's New in eCognition 9.3. So if you haven't gotten your 9.3 software yet, look into it and have fun exploring some of the new features which we will review here today. So for the eCognition suite, version 9.3, we had several motivating factors, or several primary motivating factors in our software updates and changes. First of all was the growing importance that we see in the industry of point cloud data. First of all, the growth of point cloud data integration into remote sensing workflows, as well as the oncoming devices here, new devices such as Geiger mode LiDAR, or new approaches in generating point clouds such as match-dense point clouds from photogrammetric sources. We are seeing these influencing remote sensing workflows more and more, and therefore decided to investigate how we can improve the interaction of the user with point cloud data in the eCognition project environment. Secondly, the scientific spotlight, if you will, that is being shed on machine learning, in particular on machine learning techniques such as deep learning. This was very important for us. We saw that there is a widespread use of neural networks and deep learning classifiers in the industry, and we also recognize the high potential of these techniques to solve image analysis tasks faster and potentially more accurately within remote sensing workflows, and of course integrating these opportunities into eCognition was something that we were greatly interested in. And those are two of the pillars here behind version 9.3. In addition, some of our going into a little more detail about the highlights in 9.3. First of all, what we call advanced object-based point cloud analysis or analytics, again referring to the integration of point clouds into the analysis process. We've added several algorithms for automated point cloud classification, for instance, and in the handling of point clouds within eCognition. We are currently in the process of releasing several tutorials on the use of these algorithms in terms of point cloud-based change detection, terrain model generation, and basic land cover classification from point clouds. So, and when I say point clouds, I mean LAS files or LAZ files within eCognition. Those tutorials will be made available shortly in the eCognition community for free. They include rule sets as well as sample data to look at these topics. In this webinar today, we will take a look at the topic of terrain model generation from point clouds within eCognition. Another big part of the integration of point clouds was, of course, not only just bringing point cloud, improving point cloud techniques in eCognition, but also enhancing how we view and interact with that point cloud in our projects. So we have enhanced our point cloud viewing features to enable us to get full information from our point cloud data, and to effectively combine a raster, vector, and point cloud data sets within the eCognition project environment. Thirdly here, what we call extended image analysis. We have been working very hard over the last year to integrate the Google TensorFlow library into eCognition. This is for the use of neural networks to detect patterns and correlations within our imagery. And again, trying to mimic, as we always do, how humans recognize features and objects within imagery. In addition, sometimes gets overshadowed by the deep learning aspects, but is also very interesting techniques that have been introduced into version 9.3 is new segmentation algorithms. These reflect the latest superpixel segmentation approaches and are also worth investigating when you have a chance. Finally, always striving to improve the usability of our software, and in version 9.3 we have focused on optimizing the readability of the software dialogues, windows, etc. With a 4K display, and I can tell you from my experiences using 4K with eCognition, it is wonderful. And if you don't have one, go to your boss and argue to have this so you don't have red eyes going home in the evening after working with eCognition. It is now supported and makes working with eCognition very nice in these types of environments. So those are some of the highlights that are included in this new version. And now to get into specifics, I'll start out with point cloud analytics, what is available and different in version 9.3 versus earlier versions of eCognition. First of all, we've really improved the point cloud viewer usability, making 2D and 3D viewing possible within the developer, also allowing us to combine point clouds with image data from a viewing perspective. And we've also given the user more freedom in defining how they would like to view the point clouds via various perspectives. And as we saw in this screenshot simulation here, sliding views that you can essentially step through the point cloud, viewing not only from an aerial perspective, but also varying ground perspectives within the point cloud to get a better sense of how this data looks, how, say, even a point cloud classification result may be in eCognition. Several use cases in terms of integrating point cloud data into eCognition. One that we'll take a closer look at afterwards, the generation of digital terrain models within eCognition. Here, a view that we're used to seeing, this rasterized point cloud, the rasterized LAS file in this case. We can take these point clouds, we can rasterize specific elements of the point cloud, run interpolation on them here, for instance, then creating this digital terrain model directly within eCognition. This layer is then available to use in any subsequent analysis in your rule set. We also have integrated point cloud classification techniques that will allow us, again, to apply classifications directly to the point cloud and then take this information outside of eCognition. Here in this view, looking at the point cloud with an elevation view, the essentially redder, hotter the points, the higher the elevation here also improves how a user can interpret this data within the developer project. And again, we can then apply classifications via traditional rule set classification techniques, or even automated point cloud classification tools within eCognition that will address classes such as ground, building, trees, as we see in this particular image, or even power lines and power poles. And as you can see in the screenshot on the right-hand side, this classification is physically applied to the points in our point cloud, and we can view this in the 3D viewer that is available within Developer. Another use case here is change detection. In this case, we have 2 point clouds, one representing T1 and T2. If we look sort of in the mid right-hand section of these images, we see that there is say a construction site. There's a change between these two data sets, and we can do this change detection directly within eCognition and apply it into our point cloud. So taking these information from the point cloud, we can, again, looking at the views here, this will really allow us to see the differences within the point cloud, and we see that there's some buildings and trees have been removed from this construction site in T2. What we can do within eCognition, of course, creating the DSMs, digital surface models, for each time period, we can then create a delta layer between those and then derive the change from that layer and take those classifications and apply them directly to the point cloud. So that is what we're looking at here on the right-hand side. We see that the green vegetation, these points, these are vegetated objects that have changed on this construction site, the trees that have been removed, and then the red, of course, represents buildings that have been removed from this particular construction site. So again, taking the change detection but applying it directly to our point cloud, we can then export a fully independent point cloud from eCognition that includes only the changed points in this instance. So that is some of the new functionality in point clouds. I'd now like to step into the software and demonstrate this for you. So here we should see eCognition Developer. By the way, if you're having problems seeing anything or if there are any volume problems, please let us know via the chat window, and we'll try and sort that out for you. So here we are working in Developer, version 9.3. We see that we have a point cloud loaded. This is what we are used to looking at in Developer, that we automatically rasterize the point cloud upon import. In this case, we're rasterizing the intensity values of this point cloud. Now, first of all, to review the new viewing functionality here, we can take this point cloud and we can, first of all, we will turn off the rasterized layer here. So now we just have a blank screen. And you will notice, new 9.3 users, you will notice a new icon in the menu called Point Cloud Layer Mixing. If I select this, I will get a list of any point clouds loaded into my project. So if you have multiple point clouds loaded, they will be listed here, and whatever naming convention you have chosen, in this case simply a layer 1 for this point cloud. I can then click on the Show button here to now display this point cloud. By default, we are looking at it in this render mode called height, so that corresponds to this height heat map representation. We can also control the size, the rendering size of the points. So for me on a 4K monitor, these look very small, and I can increase the size here to large, for example. This will automatically update, and now I am looking at these points in this mode here. I can then come down, click OK, and view this point cloud in 3D, or if you want to say 2.5D, we can launch. First of all, we can quickly create a 3D subset selection via this 3D cube icon right next to the point cloud layer mixing button. And what this allows me to do is simply draw a rectangle around an area of the point cloud that I would like to look at. And now we see this view of our point cloud, and of course we can come into our viewing windows and display these. when we are looking, we see this arrow on in the left-hand view window, that aerial view window. This arrow indicates from what direction we are looking at the point cloud. And if I navigate through this point cloud, so I can use my scroll wheel on the mouse to zoom in and out, I can also use the the left-hand mouse button also to scroll in and out of this point cloud. And to rotate, I can use the right-hand mouse button to move around. And as you see, when I rotate through this point cloud view, that the arrow indicating my view direction is in line to how I'm viewing this point cloud. In addition, we can actually click on individual points, just like we could click on individual image objects in previous versions. And the point that is active is not only selected here in our 3D viewing pane, but you will also see it selected in the aerial view. And when I select that point, I also can call it feature information or point cloud related feature information for that specific point here in my image object information window. So we are supporting the XYZ coordinates. We see the intensity value for this particular point, and if this point cloud had an existing classification, we would also see that class assignment indicated here in the class field. To exit this view pane, we simply come up to the close X here in the upper right-hand corner. So in addition to adding, say, the straightforward 3D selection mode, there's also a new menu for point cloud viewing within eCognition. So if we right-click in the space here, we can go to our toolbar and we can call up the 3D toolbar. This opens up these new set of tools here, and it gives us more options in terms of viewing and exploring our point cloud information. So I can first of all come here to this, what we call the 3-click 3D subset selection. And how does this differ to, say, that fast mode that is immediately available in the menu? What allows me not only to come into and create a 3D viewing a subset, but I can also do that and control the angle and size of this subset here. So again, I am no longer constrained to just simply the x-axis for this type of viewing. And again, I can view, use the mouse to rotate and explore in this point cloud. In addition, we have varying predefined view perspectives. So if we come into this menu, we can see front, back, top, bottom, left, right. So if I choose to look at this from the left, it will automatically zoom to that angle. And by default, we also have are currently in the what we call the orthogonal perspective, or excuse me, a perspective. So we're looking at the vanishing point in terms of viewing here. We can change this view now to orthogonal and really just get a view coming straight on at this point cloud, and we could say step right through this street, or imagine being able to walk down a power line corridor and see how vegetation is overlapping or potentially interfering with the power line itself. And it could be a very useful technique to explore such data. And again, to get out of this view, we can simply click close here. So I mentioned earlier, we have a use case. We can generate terrain models within eCognition. And what we are going to do here in this rule set is to not only create a DSM, but we'll follow that with a DSM, and from those we will derive our NDSM, and then we will use these to actually classify our point cloud. See here, the first step here is we want to rasterize the highest elevation per pixel. So if anybody was used to the former algorithm called LiDAR file converter, it has a new name in version 9.3 called a Rasterize point cloud. It's been changed a bit and simplified. And here I'm simply going to create a raster layer within eCognition. I'm going to take the maximum z coordinates from the point cloud and put them into a raster layer that I'm calling DSM. So we can do this. Runs rather quickly here, but at the moment I'm still looking at my point cloud view, so I'm going to turn off this view and go back into the image layer mixing. And I can see now here is my rasterized point cloud. Of course, this is not what we would immediately expect for a DSM. It contains gaps or holes, as most point cloud layers will. So the second part of this rule set is devoted to filling the gaps in this DSM layer, and we are doing this through some interpolation techniques. Like I said, these rule sets will be uploaded to the eCognition community, so if you want to then explore these in depth, you can certainly do that via the tutorial that will be made available. So what we're doing is we're simply identifying gaps in the point cloud and then doing some interpolation to fill these gaps, and finally we are just going to run a median filter to kind of smooth out some of the jagged pixelated objects and remove some of the noise that occurs naturally from this point cloud. So we can see here that we now have a nice DSM. For those photogrammetrists out there that may be listening, please think this is we've created a DSM that suits our remote sensing purposes here, and it is perfectly a perfect tool for that in this particular case. The second step, we then look at creating a DTM using some similar approaches here. I will just run this. Again, going to create a raster layer and then interpolate and fill those gaps to create then the digital terrain model as a raster layer within eCognition. So this will just take a few seconds to load. As we can see now, this is then the result. Viewing at this in a rainbow color representation here of the DTM that we have derived here. So now we have both a DTM and a DSM as layers within eCognition, and we can then come into this create NDSM chapter here for this normalized digital surface model. In here, this should be familiar territory for most of us working with elevation products within eCognition. We're back to using our layer arithmetics algorithm here, and we're simply going to subtract the DTM from the DSM to create this NDSM layer. So we can execute this, and this would then be the result of that. So again, essentially neutralizing the values of ground points within our layer, and really getting then the true above ground elevation values for any elevated objects in the landscape. Next step here, we're going to look at now classifying our point cloud. So what are we doing here? Well, we are using an assign class algorithm here. And first of all, this is just simply this is a demonstration rule set. So just to make sure that can overwrite any previous layers, I'm just assigning everything to unclassified. Now, the next step here is we have an algorithm called assign class to point cloud, and here I have entered my point condition. I would like any point, any DTM value less than 20 centimeters in this case to be classified as ground. So we can select these series of classes here. You can see there are a number of empty ones available. The defaults are here as well. So I'm going to take any DTM value less than 20, and we're going to use that to classify our ground. And I'll just run this algorithm as well. And we'll turn on our viewing pane here. And now we can come back into our point cloud. When I turn it on, I'm still in this default of height, but we notice we also have a couple other options in the rendering mode that if, for example, we had the RGB values, we can use those to for rendering, of course, intensity, but we also have the field classification. So now we have two classes in this point cloud, unclassified and ground. So we can go in and take a look at these classification results. And use just the quick 3D subset selection here. And I can then see these points. Maybe I'll increase these now to extra large. And we can see that how the ground classification worked in this case. So we've left out our cars, and we have left out the buildings, and we have successfully classified ground points within the project.
Hey Keith, this is Christian. We have here several questions from the audience concerning this example here. And the first one is if we can provide the tutorial, the example here to the audience. And I will answer this question here directly. Keith mentioned this already, that we will upload the point cloud examples to the eCognition community, where you can download the example dataset and of course the rule set, and so that you can go through the several steps to generate DTM layer using eCognition based on point cloud data. And in this context, there is also a question how the DTM generation in general works, and the question is, okay, it is needed to classify the bare soil and to remove features like buildings and trees, and this is exactly what we did here inside this rule set, using our typical object-based image analysis approach to identify elevated objects like buildings and trees, and those points will be not used then for the interpolation of the ground points in this example. There's here also another question about a user who has already taken a look to the eCognition version 9.3 about the automated point cloud classification algorithm, how it works in eCognition 9.3. And the use is quite simple. Maybe Keith, you can show the part of the create DTM layer. There is another approach written, classify ground objects, and there you see later on the new algorithm. It's called automated point cloud classification. That's the first rule inside this part. If you open this and you see there's a new algorithm, automated point cloud classification, where you can insert the input layer and where you can then define which classes has to be used for ground, buildings, poles, vegetation, and power lines. And this algorithm runs fully automatically. That means you have two ways to doing this job in eCognition to classify point clouds or the ground, using the classical object-based image analysis way or the automated point cloud classification. The automated point cloud classification works quite well, but there are reasons or regions where it doesn't work so good, and that's the reason why the combination of automated approaches with our knowledge-based, object-based image analysis approach makes a lot of sense.
Correct. So again, an automated point cloud classification algorithm is going to be much more dependent on the quality of the particular point cloud that you've loaded into eCognition. So if you have a point cloud that is not very good, the chances are that the automated classification of that point cloud will not be very representative. That is why we include both of these methods within eCognition, so you can take advantage of, again, as Christian stated, traditional rule set based classification methods in terms of customizing the classification of the point cloud, as well as having the option to run an automatic point cloud classifier, which based on some of my experience has worked very well. Even on older point clouds, older LiDAR data sets, I still had a very high success rate with the automated classification results. If there are no more questions on the point cloud tools now available in 9.3, I would move on in our demonstration to investigating the second key motivating factor here in version 9.3, and that is to take a closer look at the use of deep learning or the integration of deep learning into eCognition. So we can back out of this project. Now we're going to look at CNN and deep learning. By CNN we mean convolutional neural networks. So first of all, an overview of convolutional neural networks. I do not consider myself an expert on this topic yet, so bear with me if there are experts in the audience, if I maybe have simplified this too much. First of all, how does it work? A CNN, it has many information layers that flow into it. Each learn to detect different features of an image, and various filters are applied to each training image at different resolutions, and the output of this of each of these convolved images is used as input into the next layer to identify various features in the image. So graphically here, if we have a sample patch that we've loaded in, we can, using the CNN, that convolutional neural network, we can train based on a series of sample patches. These sample patches, it could be 100, it could be 1,000. There are certain CNNs and certain users out there that have millions of samples. And from this, we derive what is called a heat map, and this gives us that indication from a scale of 0 to 1 if that object is found within the image. So in this case, that high value, 95% or 0.9 in this layer would be a very strong match for this tree patch that we've loaded. Within eCognition, again, nothing's changed here. We're still driven by algorithms in developers, so several algorithms have been added. Several CNN algorithms have been added now to your software. For example, there are algorithms to automate the generation of sample patches. So again, CNNs typically involve lots of samples, and this enables the user, or prevents the user from having to sit down and physically click 1,000 samples for a manhole cover, for example. We can automate the sample patch generation within eCognition through a create samples algorithm. We also have algorithms to create the actual model, then to train the model. Once we have a trained model, we can then push our imagery through and apply this model to our images. So as we see in the diagram on the right-hand side, from this once we apply the model to our image, we then generate a heat map, and we can use this heat map for various classification and segmentation techniques within eCognition. So it's a wonderful integration of the CNN techniques with our existing strength in object-based change detection, and of course the automation that is available by creating and integrating everything into a rule set within eCognition. Finally, once we have these trained models, we can of course save them outside of eCognition and load them back into other projects for use to transfer the model to other project environments within eCognition. So I think we can dive right into the demonstration here. Again, if you have questions, please let us know, and we'll just get to those as the presentation goes on. So here we see a developer project. We have an image loaded to this. It's a thematic map. In this case, a thematic map in Russian of the London area. We see the Thames moving through this. The goal of this project will be to, and if I zoom in, we can give you a demonstration of what we will eventually be looking for. We see that there are churches, a great number of churches scattered throughout the city of London. They are represented by this cross symbol here, for example, here as well. And we would like to automate the identification of this particular object using CNN and deep learning techniques within eCognition. So before we go with this, we will load some ground truth data into eCognition. So this is a shapefile that represents some ground truth information of where these churches are. And from this, we want to define some map regions, which will be used for creating our samples. And we want to create regions to create a test region as well as a map region. And in this case, in the test region, we will keep independent from this. The test region will be used later for model validation. So we want to keep these. We don't want any of our test samples being confused with our validation samples in this case. So we'll execute this. We are then going to create our target class. So in this case, we're going to create objects that represent the training targets here. So we're going to apply a 3-pixel radius to these vector objects. There'll be around each target location in the map, and these will provide us by using more than a single pixel. There are just more samples available to then train our network, and this will influence how our model will learn to create a target heat map that shows these values representatively. So we will create the targets. I'm getting the signal of a question that's coming in. So Christian, please, what do we have?
Yeah, indeed, there are 2 questions concerning the convolutional neural network. The first one is, and I will answer this question here directly, is the processing of the neural network is based on CPU or GPU. You will see it later, but I answer this question here directly. In the current version, we're using the CPU only, but I can share this here that we are working on to support also GPU processing directly in our environment to train a model and also to apply a model, but the training model is the most important one here. And the second question in this context is, what are the differences between convolutional neural networks and the normal traditional supervised classification algorithm in remote sensing? The differences here is the approach. Here we're using a neural network classifier compared to other classifiers like key nearest neighbor, things like that. And neural network classifiers are not really new, but we have now the computer techniques, the power of the computers to execute such complicated training processes, and the applying, that means the execution of such approach classification techniques. The main differences between the traditional one and the new one is to create samples, and this is exactly, or sample patches, what Keith is showing now in the next minutes, because you need more samples compared to the traditional approaches to train. It makes sense, only sense with more samples, sample patches to train this classifier approach, and also then you have to create a model and to apply a model and to train a model between the two steps. There's no big differences. That you will see it a little bit later. That's all about the current question. Okay. Next one we will see later.
Excellent. So while we've been answering those, the create target class as chapter has run, and we can see now that we have an image object. We've put a buffer around those initial ground truth vector layers here, and we've created these image objects that will then flow into our target to create our sample patches that will represent the target samples. In addition to creating patches for targets, we also want to create a class for non-targets. In this case, we're going to classify the dark areas of the map, since these have the highest potential for conflict with our church symbol, as it is also dark. And what we are going to do here, we are going to simply apply some Gaussian filters and then use a threshold-based classifier to identify then the dark regions of this thematic layer. So we can execute this and take a look at the results. These objects will then be used to train to create non-target sample patches. As you can see here, you can see the dark pixels versus now our target objects here, or excuse me, our non-target objects versus the target objects. The next thing we want to do, because we want to generate a test region within this image, and I'm simply going to remove the classification from this test region. If I then zoom out, we now see that this region of our image will be used for testing, and it is completely stripped of any classified image objects at this point. Finally, we are going to segment apply a chessboard segmentation to our objects here, our classified objects. This will use a chessboard size of 1, so to generate single pixel sized objects, which will then give us a greater number of sample patches in the next step. So we can execute this step as well. I should mention again that we have this tutorial for how to use convolutional neural networks within eCognition. It is a tutorial, and it is currently available in the eCognition community. So if you'd like to download this rule set, as well as the input image, it comes as a package, and we also include a step-by-step PDF, not only what processes we are running, but explaining also the background and the theoretical concepts of using these algorithms within eCognition. So that chessboard segmentation is run. If I now zoom back in, here we see that I now have a single object, or 1 pixel by 1 pixel object here in both the non-target and target classes. The next step would then be to create these sample objects. Because this takes a few minutes, I ran this ahead of time, but what we can certainly look at are the algorithms for CNN within eCognition, or for deep learning within eCognition. First of all, you will find them towards the bottom of the algorithm list. They are all identifiable through this network symbol, or find it looking like a spider web. These are all the algorithms that are involved in working with convolutional neural networks within eCognition. So what we have here, first of all, is an algorithm to generate labeled sample patches. In this case, we're going to create 8,000 sample patches for our target class. This is done randomly. We're randomly picking from all the pixels, so all these the single pixel objects from our image object domain. So in this case, we will randomly select a pixel classified as target and create a patch, a sample patch from this object. This sample patch size is going to then be a 22 by 22 pixel sample patch that is then around the center point, so that we are randomly selecting the central pixel. We're going to select 8,000 of these and then create a 22 by 22 pixel patch around each of these. And we are doing this again also. What layers do we want higher? If we have multiple input layers in our project that go beyond, say, just red, green, blue, we can select the image layers for which we want to also correct these sample patches. And in this case, all of these sample patches are going to be stored in a default folder here called samples within in our project area. And we will run this not only for the targets, but as you can see, the next step here is to also apply this and create sample patches for non-targets. In this case, we are going to create 32,000 sample patches for non-targets. Why are we going to collect more here? Well, simply because our image contains much more non-target than target regions, and we would like to consider this when it comes to misclassifications to remove these problems. But again, everything else stays the same, 22 by 22, and we're also going to be using the same image layers. Like I said, I ran this ahead of time, and what does this look like? Well, it adds a folder to where I have my project, in this case called samples. Now if I look in this folder, we have then just by default the naming 0 and 1. The folder called 0 corresponds then to the target. So you can see here that I have a lot of sample patches available corresponding to those church symbols. And then in folder 1, I then have all sorts of samples patches for non-target within the image. So that's nice. That was run, and the next step would then be to, once we have our sample patches, like we showed in the diagram, the next step is then to create our model. And for this, we are going to be using an algorithm called, excuse me, just have to open it up. This is called then create convolutional neural network. And here, the algorithm will define, again, the size of the samples. Here it's going to be a 22 by 22 pixels, as well as the number of layers. In this case, we had 3 input layers, so we will use these 3 layers again for training this model, or excuse me, creating this model. We also need to input our model classes. In this case, we want the non-target and target classes here. And for this, we are going to create some just one hidden layer. For each layer, the size of the convolutional kernel needs to be specified, as well as the number of features that will be generated, and whether or not we want to use a spatial pooling within this model. So in this case, we are using a kernel size of 13 by 13, We're going to use 40 features, in the CNN, and we have set to yes to use the max pooling for this step. And again, this has been run ahead of time due to, and once we have then created this model, we ran it ahead of time just to avoid having too long a delays here in the webinar. We can then, once we have that trained model, or excuse me, once we've created our model, we can then train it. So when it comes to training, we have another algorithm here called trained convolutional neural network. And here we have to define, first of all, our sample folder. Which samples, where are these samples to use for the training? And we also need to define the learning rate. In this case, it's going to be that 0.0015, as well as the number of training steps. In this case, we're taking 5,000. And then finally, the batch size. This is the number of samples that will be used at each training step. And in this case, we've gone through and are using 50. Important for training, the learning rate is a particularly important parameter. It defines the amount by which weights are adjusted at each iteration of the statistical gradient descent optimization used by eCognition. We don't want something too small. We also don't want something too large. So it's typically recommended a gradual decay of the learning rate is common practice here. We've looked at this ahead of time. So in this case, we determined that this learning rate of 0.0015 or 0.0015 was optimal in this case. Once we have that the trained model, now we're ready to actually apply this apply this model, so we can push our imagery through the model. And you can see here again that there is an algorithm now called apply convolutional neural network. In this algorithm, we again need to select the image layers to use. So we continue to use our layers 1, 2, 3 here. And important also is for which class we want to create this target heat map. In this case, I'm not interested in a target heat map for all those non-targets. Well, I really just want to look at my targets. I want to find those churches. So we're going to create this target heat map for the class target. So we can run this whole section here. And while that's running, Christian, are there any more questions flowing in?
Yeah, we have here indeed several questions. First one is more or less a general one. Why we're using here such an artificial image and not a typical remote sensing image to demonstrate the CNN capabilities in eCognition, and the reason why it's to simplify the whole approach and the learning curve here, to make it easier to understand how it works. To find the crosses is a very simple task, so that you have a clear understanding which steps here are really needed to create the sample patches, to create a model, and bottom line to train a model and apply a model. And that's the reason why we selected this example. Yes, of course, we had here several questions. The whole workflow, the whole ID, and the usage of the algorithm works on any kind of image data. That means image data from satellite systems or UAV systems, airborne systems, or simple pictures, whatever. That's hopefully more or less clear, and Keith explains the different steps which are needed to create samples and use those samples and input to train a model, to generate a model, and to apply a model in this context. There's also a question: is it possible to load a pre-trained network to the eCognition system? Yes. you will see it also a little bit later that we can save a trained model very easily to the file system, and you can load the trained model again to the eCognition software. We will provide also some detailed information which parameter and name we used inside eCognition for such TensorFlow models. That means in general we are supporting all kind of TensorFlow models also created and trained outside eCognition. That means if you are already using Google's TensorFlow library, you will be able to load them with some changes the files also directly into the eCognition environment. Here's also another question: if we are supporting beside these convolutional neural networks also other supervised classification methods, and that's clear since version 9 and version 9.1, all the versions before, we're supporting random forest and support vector machines, CART, that means decision trees, supervised classification methods, and the nearest neighbor approach in our software. That's all currently from the questions.
Okay, excellent. While we've been answering those questions, the model has now been applied, and we have our heat map that has been generated for the class target. And we see here that there are red dots. They generally appear in the image locations that that contain or resemble our targets or our churches, and we can see those this relationship very nicely if we look at our view split window. We can see that those red dots here, those heat blooms, if you will, they are corresponding very nicely to the different church symbols in our thematic map here. Like Christian already mentioned, in terms of transferring this model now into other projects that you may have, the final step in the first part of this demonstration is now to export our model or save our model outside of eCognition, and we can do that here through the Save Convolutional Neural Network algorithm. And we can simply execute this. It then creates a series of 3 different files outside of eCognition that are consistent with the Google TensorFlow format. So you'll have a metagraph file which is storing the network architecture, as well as 2 other files that represent the weight settings that were used or affected by the training of that neural network. And I believe if I come back into my File Explorer, I can see now here is my model, and here are those different files available for you outside of eCognition. Believe there is one more question that has come in the meantime.
Yes, there's a question if convolutional neural networks are slower than other classification methods used in eCognition. It's really hard to answer this here, but in general, yes, because to train a model takes a lot of time because we're using thousands, or it makes only sense using thousands of sample data sets. That's the reason why to train a model takes a little bit takes more time compared to other approaches, but to execute a trained model it takes only some seconds, like the other methods before. But the approach itself is more time-consuming, but it's quite good. Now we have the computers to doing such neural network classification approaches inside eCognition, which was not really meaningful 10 years ago. Things like that. Okay.
So that wraps up this, I guess, what we'll call lesson 1 of this tutorial. Again, available in the eCognition community. Lesson 2 is actually going to then now derive objects for that represent our churches. So convert this heat map into an object, and we can run that this section here, we're going to be applying some general smoothing to this heat map layer, and then extracting local maxima. The steps are all included in the tutorial, and then we're going to be using some threshold-based classifiers, and of course then converting these objects that we identify as churches into a vector layer. And if I zoom in now, we can view these results. Just turn off the split window in this case, and now you can see that I have an object here. We've just dropped a circular object around each of our church symbols. And finally, what we ran was we wanted to have some statistics on the error rates and the falses or misses here, and we see those in the image object information list here. So we see there's 7 errors, 5 falses, 2 misses, and we had then 89 hits here, 89 objects that represented those churches. If any of our users are interested then in comparing this, say, to other techniques available within eCognition, this rule set also includes a comparison to template matching results. And I can tell you we've run this ahead of time, and we're looking at decreasing the error rate from around 22% in template matching to just under 7% with the convolutional neural network approach. So in this image analysis situation, CNN or deep learning techniques are very beneficiary and have yielded a better result than what was previously available in eCognition if we think of the template matching approach. So we definitely see the benefits of integrating this deep learning technology into eCognition, but more importantly, being able to combine it with our rule set strength and the automated approaches that already exist in eCognition. Again, not solely depending on the outcome of the deep learning or the convolutional neural network. So we can go back into the presentation. That wraps up our demonstration of working with convolutional neural networks in eCognition. And it brings us to the end of our webinar. To summarize version 9.3, we have added, again, the 3D point cloud analytics, really improving how the user works with point clouds in form of the viewer, being able to understand what is going on in the image. And on top of that, we've added deep learning technology just to enable more robust and accurate analysis for a broader range of applications within eCognition. And I think we can field a few more questions before we have to stop for at least our evening here in Germany. Christian, has anything else come up?
Yes, we have here several open questions. The first one, the question is for you. Is it possible to get a link to this webinar? That means is there a recording available after this webinar for all the audience, the participants?
Sure. The webinar, all our geospatial webinars are recorded and made available, if not directly after the webinar, maybe there could be a short delay, but they will be available online, and within the archive you can go back and view any webinar that we've done in the past. So yes, those will be made available.
Okay, and there's another question concerning the convolutional neural network. Is it possible to load a pre-trained classifier model into the eCognition environment? So if it's a pre-trained TensorFlow model, yes, we can load these. It is possible to load them into eCognition. Yes, here's also this question is quite often here. Is it possible also to load an external TensorFlow model to eCognition? Yes, it is. If it's created inside eCognition, then it's very easy to load it directly. If it's created outside eCognition, but the user used the TensorFlow library itself, he or she has to add some file names to the model. We will be providing this information as soon as possible so that you can also load your pre-existing models which are created outside our environment. We're supporting fully the Google TensorFlow library. Okay, I go through the list and select maybe the last one. Okay, there are... Okay, that's all here from my list.
Excellent. If anybody does have questions that pop up post-webinar, you can certainly let us know. You can contact myself directly here, my email address, or if you want also the help of eCognition support, please contact support@ecognition.com, and they would be more than willing to answer any questions that you may have in regards to the new software or certain features available within the software. That being said, thank you for listening and taking the time out of your day. I hope you enjoyed this webinar, and stay tuned for future webinars coming up in the new year. So everybody, happy holidays, and we will see you next year.